Thank you very much for coming to our presentation. My name is Aleix Llenas. I'm a physicist and doctor in optical engineering, and I'm currently working at Ledmotive, which is a company based in Barcelona that designs multispectral light engines. This talk will cover a set of spectral tools that we have developed to have a fully human-centric lighting approach in new installations and lighting designs. This will be the outline that I will follow through this presentation. First, we will talk about light and how important it is to consider the whole spectrum of light when designing spaces. Then we will discuss different spectral tools needed to design installations, taking into account the guidelines for human-centric lighting. And finally, we will discuss two different applications or cases when using these spectral tools will be important. So let's start. First, consider two types of light in our daily life, natural light and artificial light. Natural light is a mixture of sunlight and skylight, modulated by the interaction with the atmosphere. Daylight is broadband with energies at all wavelengths and is dynamic. Its spectral shape and magnitude changes from morning to afternoon, leading to changes in luminance, lux levels, and what we colloquially call color. We humans evolved under these natural lighting conditions for millennia, and our body's physiology is synchronized to the natural changes in light over the light-dark cycle. But lighting installations in buildings and offices are usually static and specified in terms only of their effects via the classical visual pathway, for example, chromaticity or brightness. Moreover, classical lighting technologies are quite different from natural light. Fluorescent lamps, for instance, white or tunable white LEDs have a spectrum that's different from daylight, generally being less broadband, being more limited in color range, and yielding poorer color rendering and quality. That means inducing different color appearance of objects compared to daylight. Today, we spend most of the time in indoor spaces with light sources lacking the spectral properties that daylight holds, and this has consequences. Indeed, it is now recognized that the spectral variations in light not only enable us to see via the classical visual pathway, but also elicits non-visual effects, including on emotion and cognition via a distinct neural pathway. And it is important for health and well-being to take these effects into account. The non-visual pathway begins in the intrinsically photosensitive retinal ganglion cells located in our eye, which contain melanopsin, a photopigment directly responsive to light. Melanopsin spectral sensitivity peaks at 480 nanometers in the short wavelength region, blue, and these signals from the IPRGCs ultimately affect our circadian rhythms or body temperature, attention, sleep, heart rate, brain performance, and more. And also they interact with the classical visual pathway in ways that we do not yet understand. So when designing lighting spaces, it is important to consider the non-visual effects of light, and that means the melanopic lux and that the whole spectral shape of light are key. And as we have seen, if the spectra of the classical lighting technologies is different from daylight, its properties underneath will be also different, even if both lights are white light or have the same chromaticity. The properties of a light ultimately depend on its spectral shape. For example, color quality, and here we can use as indicators the CRI or the TM3015, or for example, the non-visual effects of light. And here we can talk about the CS or the melanopic lux, or the damage potential for artworks, the efficacy in lumens per optical watts, and all horticulture indicators. All of them ultimately depend on the spectrum of light. All these properties will be affected by the different spectral shapes that our artificial light will have, and not by its color. And therefore, having a light source able to modify its spectral shape at our will in an arbitrary way will be the best tool to enable a truly spectral lighting paradigm and to start designing spaces with the spectral properties of light. And one example of spectrally tunable lighting system is the VGAU7, that is a small light engine designed and developed by Ledmotive that has 7 different channels and is easy to integrate into more complex optics like downlighters or projectors. By tuning the amplitudes of these 7 different channels, we can design different spectral shapes and match any possible light. And this is not a tunable white solution nor an RGB light bulb. This is a full spectral light source with the best flexibility to create visible light spectra and control the light levels. These four examples show how we can tune the different channels in order to match any target spectrum. Daylight D65, an incandescent spectrum, a black body of 7000 K, and the melanopic spectral sensitivity function. And multi-channel light engines like the Vigo 7 are key for human-centric lighting designs. Consider melanopsin, for instance, which peaks at 480 nanometers. With a spectrally tunable light source, you can provide high doses of melanopic lights in the morning to wake up and low doses in the evening to favor sleep, with the color or CCT desired at any moment, or optimizing any other light property. So in the case of RGB or tunable white light sources, there is a strong limitation, and you can only have a limited number of CCTs or color, which is also limiting its properties and nothing else. So we have seen that spectrally tunable lighting systems are important for human-centric lighting designs, because then you can design spaces with the whole spectral shape of light. But besides this, what else is needed? I can think of at least two more things needed. One is a small and precise light sensor to measure the spectrum of light, and the other is a fast calculation server to analyze all light properties in real time. And let's take a close look. When is the light spectrum measurement needed? For instance, to assess lighting installations and ensure always the best light quality, or in photography, to assess the chromaticity, or for video makers to ensure that you always use the same kind of light in your settings. In museums, to prevent the degradation of pigments and to use the same illumination as the artist used when the artwork was created, or for example, for scientists interested in spectral analysis, or to copy daylight and bring it into indoor installations, as we will see later on. Finally, who needs to measure light? As mentioned, lighting designers or architects, researchers, filmmakers or photographers, art commissioners, or engineers working with light and lighting systems. And with that end in mind, we made the Photon Phi, which is a pocket-sized spectrometer designed to capture and analyze all light indicators. It can be used for light quality measurements. It works over the Internet of Things, meaning that it can send the measured light through wired and wireless networks, making easy to access. And it can be used for spectral quality inspection, for flickering measurements, for color science, circadian rhythms, health, museums, and horticulture indicators, and to measure dynamic sequences of light. Its main functions are measure and analyze any light, from visually seeing the spectral power distribution to checking the CCT or color coordinates, the quality through CRI, TM3015, or other quality indicators, the melanopic lags or CS, and more. And finally, store and send the spectra to your lighting system in a very easy way, always through your smartphone. Some technical aspects, for example, that the wavelength range is in the visible part of the spectrum from 380 to 780 nanometers, that it can measure a wide range of illuminance values, and that the connection is through Bluetooth. Let's see now how we can use these tools to design better human-centric lighting spaces. This is the first application. This scenario allows any user to take all the necessary spectral snapshots by pointing the spectrometer to the light source. The application in your smartphone will display the spectral power distribution of light and analyze the spectral data and derive all the properties from the spectral shape and intensity. It is easy to use and has a friendly visualization that will help you assess the light quality in installations or to store your favorite light settings for future reference. This is the second application. This scenario represents the full cycle of the Ledmotive ecosystem. First, we measure a light spectrum with our spectrometer, in this example, a sunset. And then we send the spectrum to be played, and we select the spectrum to be played and send it to the luminaires and fixtures containing the Ledmotive light engines, mimicking the same spectral shape and the same color in our indoor installation. This can be done without any delay, like in a setup that we did in collaboration with Arup and the Newcastle University. Here, the spectral sequences are being captured by a spectrometer and played by the luminaires and fixtures containing Ledmotive modules simultaneously in real time. This application has been tested in an office environment where the spectrometer was located on the rooftop of the building and was sending the information to the lighting system inside the office. The spectrometer was gathering spectral data from the sun through the day and playing the best spectral match and color inside the office, therefore copying daylight properties and bringing a novel human-centric lighting approach for office installations. We did take some measurements to test the system performance before starting this sequence, and these graphs show the comparison of the spectral power distribution curves inside and outside, where the blue lines are the spectral power distribution of the light delivered from the luminaires inside, and the black broken lines are the measurements of the spectral power distribution from the sensor on the roof. So these measurements basically validated the performance of the system and confirmed that it was doing what we were looking to achieve. We also did comparisons on the CCT between the daylight and the light inside, and both lines closely overlap. We also targeted to achieve the variation in illumination levels at the desk. So we wrote a script to mimic the variation in illumination of daylight as well, but clamp it inside to make sure that the luminance levels at the desk never exceeded 500 lux and also never got below 300 lux. When implemented, we got very positive inputs from office workers toward this real-time daylight matching system, highlighting the importance of a change in spectrum through the day and to create a more vivid and more lively environments. In summary, we have seen that a truly human-centric lighting design uses three things. First, a multi-channel light source to sculpt any light spectrum and to design spaces taking into account the non-visual effects of light. And then a lightweight spectrometer and a calculation server to measure and analyze the light spectra and to assess the best light properties for each end user and for each application. Thank you very much for your attention.